That's how technology is. Makes a fool of you. That's how smart people is. All right, so as promised, connectivity. We looked at connectivity on the ultrasonic graph. This is slightly more. This model, I'll put a star to it. This is not exactly Gilbert's this model. So in the Gilbert this model, what we did was locations were distributed over the polynomial process with density. Here we can't handle this because connectivity with high probability won't be there. So instead, what we'll do is we'll consider disk of radius 1 and we consider endpoints. Uniformly randomly. Located in B 0 to 1. And around each point will draw disk of radius R of n, and all points which are inside are defined to be connected both ways. So what are we interested in? The smallest. So the question really is smallest of n that guarantees connectivity. By connectivity meaning that I can reach any node from any other node. So keep in mind the distinction between a point process and what we are doing here. They are very related, but not the same. We'll in fact use some connection between them to actually do the analysis. But be mindful of the fact this is not a point.
The difference is the distribution of
position
of points. Right? Here they are uniform and there it was with respect.
So yeah, so if you condition, so in a point process, this is the property. So let's take the same P01. If you condition that there are n points, so number 0, 1 is n, then these n are uniformly distributed. But nobody tells you that they're exactly n's. That itself is a random point. So that's the basic distinction between what we're doing. Here we're assuming that there are exactly n points, which are uniformly randomly distributed. So the way to think about it is somebody's telling you that there are n points when you started with the polar point. So you should really think of it as a polar point process with density n. And somebody told you there are exactly n points falling in that disk of radius 1. Then they're equivalent. Otherwise, this is the random quantity. But on average, you expect something very similar to that. All right, any other questions? Oh, so what will we do? We discussed strategies for both last time. So at least tell me one side strategy. So when I say smallest, I have to tell you that if Rn is below something, there is no connectivity. If Rn is above something, there is connectivity. And for this, we'll actually show that the thresholds are exactly tight. And the illusion I gave you last time that if you think of this as boxes of size of, let's say, length here, S. So if I take S is equal to square root log n over n, with high probability I can show that there are roughly log n points in each of these boxes. And once I have log n points and I choose S to be smaller than, so what other condition do I need? So suppose that independent of Rn, I just did a, I just drew a grid with side S. The S was roughly square root log n by n. Using Chernow bound, you can show that every single such box contains roughly log n points with high probability. Over all of them, not just one. So union one. Now, if I want connectivity, what should I really do? All I should do is select R of n to be, let's say, square root 5 of S. So if two neighboring boxes, the maximum distance between this and this is at most square root 5s. So if R of n is square root 5s times this, and every box contains log n points, I should be able to connect to it. So roughly the answer I should expect is square root log n by n. That is what really I should expect to have. Precise answer will derive how. But intuition to keep in mind is that roughly if you have square root log n by n, it is sufficient. Question is anything below what will happen? None of those inequalities will work, but is it just the limitation of the inequalities or is there something more fundamental? The idea is that if I choose S to be square root log n by n, roughly there are log n points in every single box. There are so many boxes there. Simultaneously, there are all these boxes contain log n. And if I take my Rn to be square root 5 times S, I can directly I can reach every node from every other node. So at least on the upper bound side, as long as Rn is roughly log n by square root log n by n, I should do that. Question is it necessary also? So that's the first thing we'll try. And if it is smaller, what goes on? So essentially, we will try to control the probability of isolated nodes. We'll say if the Rn is smaller than that, in fact, the probability of isolated nodes is sufficiently high. And that implies no connectivity. It's a stronger condition. So main theorem, just two parts. So this model is called, so I will tell you the distinction I am going to keep. So this is the model where n points are exactly located uniformly randomly in a disk of radius 1. G n comma Rn is a graph where any two nodes are connected if there is a radius of Rn is connected. When is equal to C of n divided by n. One n tends to infinity. This is the punchline here, and only below. We reach slightly more than square root log n by n. That's all this theorem is telling. So the radius is scaling as square root log n by n plus something which has to go to infinity. So this can't be very small. Overall, it can, so Cn by n can go to 0, but the Cn has to go to 0. That can't be a constant. That's all right. Statement clear? So G of n comma Rn is the model we are working with. Whenever I want to look at the Poisson point process, I will put a subscript P to the graph. Just to make the distinction clear. So this part I don't need it. So only for the sufficiency part I need. Okay, so move for the necessary part. Only if. So let probability ISO the probability ISO. So if I do bound some very simple things. This is obvious. So P ISO is nothing but that there exists at least one isolated. So that means that at least one of them is isolated.
Yes.
Okay. Now, what more interesting can you say from here? Can you somehow connect a single isolated node and a pair of isolated nodes? So I want this probability to be written in terms of
Yes.
pair as well as singletons. So think of the event. I is an isolated node and compare that with I is the only isolated. The distinction there. So I is an isolated node. And I is the only isolated.
We should subtract the yeah.
Okay, very good. So can you tell me exactly?
And
So probability that I is an isolated node.
this means only plus. And
You want equality or want inequality?
because there will be higher data you take greater.
Okay.
Then only isolated plus higher only.
Okay. And plus
I and some other. No good. See.
is that what I wanted? Okay, write this through.
So this is an union.
Sorry,
So that thing is union of this.
there are many other things also.
That's what the
Triplets and groups of four and so on and so forth. This is the only one. There's only possibility, the only one of this. Here, I'm counting two at a time. Essentially, use that here. So it is minus sign. But why am I doing this? That's the question. I want really to control this probability. What will I get by doing all this? The complex probability is the only isolated node. This is the complicated beast. You think about it, because I have to make sure that everybody else is connected. That's a problem. I don't know how to handle it. I is disconnected, I is isolated, but everybody else is connected. So I have to go to a graph where there are one less number of nodes and do all sorts of difficult things. But this is something simpler. How much is this probability? We can actually write down exactly. That I is isolated. Which is I is isolated. There's no sum, right? The summation is from the outside, that will worry about later. But this one is a simple event. That node I is isolated. That means within a radius of Rn from it, there is no other node. So all n-1 nodes lie outside. What about this one? I and J simultaneously are isolated. So definitely I and J are at a distance of more than Rn from each other. That much is clear. And both disks are empty. You get multiple events to actually control this. This is a complicated event. So that is why we are doing this. So using this, I can now. Let me call this QI and then so this is QI minus do you want to say? So far so good. Very elementary stuff going on.
What are QI?
This is QI. This is ZI. IDRS. What is QI? QI simply 1 minus pi r square n to the power n minus. What's ZI? Remember the event is R and J. There is some I. So this is radius R and this is J. And both of them are isolated. What does it mean? That both these disks are empty, as well as the distance between I and J is also at least R. So can you write ZIJ? So let's say the distance between I and J is V. What we know is that ZIJ is strictly greater than R. That kick off two events, one belonging to and to R. So there are only two possibilities. Either the distance between them is between Rn and 2Rn, or it is strictly greater than 2Rn. So can you write ZIJ in terms of these two disjoint events? See, what is happening is for the rest of the nodes, the area is not 1 minus pi r square, where they all can lie. Because of this, it's further restricted. So under this condition, what is that is, and under this condition, what that is. Here I only care about I isolated. So I just looked at the whole of the rest of the areas.
So for the second condition, it will be 1 minus 2 times pi r n square
Okay.
whole to the power n minus 1.
2. Only n minus
N
2.
minus.
Okay. But what about these guys?
If the distance is.
But they also have to be counted for.
Into 1 minus pi r square.
No. The fact that dij is greater than 2rm also has to be accounted for. See, this essentially what it means is that the disk of radius 2rm is empty. That's effectively what is going on. The distance between them is larger. You can compute this, it's not very difficult. Zij. Essentially, not precisely, but otherwise, it's 4 pi r square n minus pi r square n times 1 minus pi r square to the power minus. So this belongs to the first figure and plus 1 minus r square. This you can check. The constants are not very important. That is what the areas you can quickly get restricted. So the first term belongs to this interval, the second term belongs to 20 edges greater than. All right, so what have we got? Finally, the probability of isolation is greater than or equal to from 1 to n. Actually, doesn't depend on the identity. And this is the under. These. I'm just putting those terms in here. Now remember the theorem we want to prove that r square n better be log n plus c of n by n. Any idea why it is coming from? So essentially what we want to show that probability of isolation is going to a constant unless Cn goes to infinity. Because we know that probability of disconnection is at least as much as probability of isolation. And if this is going to a constant, connectivity cannot go to 1. So why is it that this quantity is bounded from below if Cn goes to 0? Or Cn doesn't go to infinity, doesn't goes to. That's all really we have. Now it's purely algebra. All the geometry has been accounted for. All the thing of it is calculus. You have to use some inequality, but at least see through. This is the relationship. But if C of n does not go to infinity, what is going wrong? That's all really there. Yeah.
Back to the previous page. There we have PISO is written equals to only isolated node. And that is less than equals to QI minus GI. That is GI.
Yeah.
So how can we say that that is greater? I mean, when we are extending,
No, sorry, ask correct question. I'm not following.
we
This one?
no, that one. Next one. And that is equals to less equals to QI minus ZI.
Yes.
But in the previous thing, the inequality is PISO beta equals to that thing. But that is less or equals
So
to.
this one.
Yes.
So this direction is the problem.
Hmm.
Okay.
So that is right, but
Okay, that is right. So then
how
that
can
is
we
wrong.
substitute that.
Okay. So did I make a mistake? This is not right. Yeah. That's the mistake. That should have been obvious. This is an isolated role. So it includes that the only one as well as everybody else. Right? This doesn't preclude the possibility that I'm the only one. This precludes the possibility. So definitely this has to imply this. So clearly that other direction is wrong. Not clear. I am isolated means what? I am isolated. Somebody else also might be isolated. No, not don't care about others. So it's including. So this can't be that I'm the only isolated one. Right? It includes the fact that I'm the only one as well as some others also isolated. So this implication is the right direction. So that was wrong.
But only isolated is stricter.
Yeah.
So it's
So I'm the only one.
it should either be less than or equals to.
But so the rest of them are here. See, what are all possible ways in which I can be isolated? I am isolated. I'm not telling you anything about other status. Here, I'm telling about everybody else's status also. So this quantity and this quantity, if you only compare, you're right. But then there are so many other events which are also there. If you just particularly compare them, then that is wrong. Thanks for pointing. Okay, so any algebra to suggest that if pi r square is log n plus cn by n, where cn is not going to infinity, why should this get bounded? So some inequalities. Next. That's the first inequality in office. Pure algebra, so now. So that would be point of this. So nothing really interesting about it. All it's saying is that if you pick these values to be log n plus n by n, this inequality holds. Just plug in, look at the remove the exponent function. 1 minus 1 over n to the power n. That's all there is. Everything inside it. And one more inequality I need, which is also basic. Where is the one? It's actually you are already done. Already. Down to 0, 1. Theta, 1. It's just easier. That. First part is straightforward. Second part is playing anything more. This you already know. But minus t is less than equal to. What you're saying is for any theta greater than 0, there exists with t0. So that is also bounded by. So the theta goes inside. This is going in this direction. This is going in the opposite direction. With the theta setting inside. The theta is greater than 1. So sufficiently large theta to make sure that this quantity is smaller than 1 minus t. So these are the basic problems. Okay, so suppose I give you both. Can you go back to the previous board and try to see what we are trying to do? So the first proposition controls this, the first one. What about the rest of the terms? Everywhere the identity of I and j has been lost. So you can essentially replace the sums by n times n minus 1 here and n here. It doesn't really depend on I or j. So this is simply n times this, and this is n into n minus 1 times. So that should help you to get rid of the summations. So essentially you can replace first term by theta times e to the minus c. That's first term as it is. What do you do for the second and the third term? That's what you should think about. Order wise, what are these? N into L minus 1 into what? So there is a R square N, and then this is 1 minus, so think of this is 1 minus T. What is the less than equal to e to the minus T real? But it's exponentiated. So e to the minus N minus 1, N minus 2 times T. That's what you do. So this is N into N minus 1 into R square N into e to the minus N minus. That's what both of them are really looking at. So what should I do? Let's go to the computation. We want to make some obvious observations.
So we get another input.
So this is anyway in the right form already. It's showing up as e to the minus theta cn. That's roughly the right thing to do. I want this also to be in similar form. Why is that? What is the order wise? Think of the order wise. N minus 1 is roughly n square. Then there is 5 square n r square n. Right? And there is n times r square n. That's what roughly the order is. What is the overall order? Where r square n is log n plus cn by n. That's all you have to notice. There's nothing really interesting about it. So this one n will be cancelled by this. What about this one? Here also you'll get e to the minus n times log n by n. N will cancel, log n will remain, and e to the minus log n is nothing but 1 by n. That will take care of the another n.
It will be something like log n square by e to the top.
Okay, that square will not going to matter then. This 2 will just pop out. See, r square n is log n, not square.
Okay.
Square already is log n. Remember the radius. Okay, that's why I gave you that simple thing. Square root n. So radius is square root of log n. Okay. So what are we getting? You're getting n into n minus 1. This will give you log n by n. So one n will get cancelled. This will give you another n. You cancel this. What you'll end up getting is something like log square n here and e to the minus n.
Log n times e to the power.
Yeah.
Log n.
Log n times e to the power. Yeah. But that will cancel off. What you'll end up
And
remaining inside is exponential of minus c of n. That's all you're getting. So if you do this, what you end up getting is this term in every theta c. It's got c of n. So that plus oh, now can you complete the proof? For some pi greater than equal. All I'm doing is just evaluating this expression at r square n is equal to log n plus cn by. That's what it is. This is what we get. Now can you just complete the argument saying as long as cn doesn't go to infinity, this is going to be lower bounded by n.
we had done that exponential minus p n and n, right?
Right. So there will be few more cancellation. So the r square n will be log n here. And e to the minus, so what exactly will be there? Sorry. Okay. It should be right. Now give me the punchline. Right? Now is it that I need c of n go to infinity? That's essentially what we. Alright, sorry. If it doesn't go to infinity, what will happen? This will essentially some more little work is needed. I'll do that, but more or less that is what is going. That is difficult to I'll tell you what more. It's not done yet. In principle, we are done. That is what we really wanted to show. That is why I want CN to be unbound. So go to the next board and do all the extra work. So by definition, PD, which is the disconnection probability, 1 minus PC, connectivity probability is greater than equal to probability of isolation, which is greater than equal to theta. Where is the minus there? So there's a minus over there. This board. There is minus here. So this is not plus. Okay. So let be bounded. And in a particular, let's see C bar. And going to C of n is C bar. What can I do if I do this? Then can I make a property that for any p greater than 0, C of n is greater than equal to C bar plus p for n greater than. By the definition of the limit. The limit C of n is C bar. So C of n eventually has to be very close to C bar. I'm just inserting a p so that it is greater than equal to n, which depends on. Now I'm essentially going to replace C of n by this. By noting the fact that probability of isolation is monotonically increasing or decreasing with respect to C of n. So if C of n increases, what happens to P of D? Disconnection decreases or increases? It's monotonically decreasing. So I can put this bound here without changing anything. So Pi ISO still greater than equal to theta x. That's true.
What is N of P?
What is the limit definition? Just recollect that. So C of n is equal to C bar. Essentially means that for any epsilon, the difference between C of n and C bar is less than epsilon. For any n greater than n, which depends on epsilon. So I'm just introducing the phi here. So the gap is at most 5. For any n which is greater than n, that depends on. So for pick in our typical language like epsilon, so you just think of this as epsilon, where for large enough n that depends on epsilon. That's all it is. Okay, so now what? Why am I done? At least now give me the punchline. That if it is bounded, this quantity is also bounded. If C bar is bound. So in conclude, you put a question mark as to that, you go back home and do it for yourself. This implies that C bar is hold on. The right word to use. That never goes to zero. So that is why this limit cannot exist. It has it better go to infinity. How it goes, it doesn't matter. We'll show another direction that is also sufficient. That how it goes to infinity is immaterial. As long as it goes to infinity. All this is gory details. I'll keep referring you back to this picture. Keep that in mind. That's really giving you all the intuition bonus. That if the radio range is roughly square root order log n by m, should be sufficient. All this is to make sure that all the epsilons and deltas are counted. That's all there is. Essentially, that's what the theorem is telling. Is square root log n by n, but with a small fudge factor. So what's a little bit extra. That's all it needs. If this is zero, it doesn't work. That's the point. Okay, so now let's go to the sufficient. One way to build a proof for sufficiency is using the term of one argument. Here is something which we are going to do by coupling the Poisson process and the uniformly distributed parts in the zero. So now the sufficiency part. So just make sure that it is properly. So G of n comma Rn is the graph which I am interested in. G P of n comma Rn is the restriction of PPP. This let me be very clear. I'll keep using GP again and again. G is the graph which I am interested in. GP is the graph which is the restriction over of the PPP over. That's with density n. So here is the proposition which I am now going to prove. I don't know if you can do this reaction for mine. If you're very interested, I'll give you the reference. The probability of disconnection in the graph GP of n comma Rn is very close to 1 plus gamma times probability of isolation in GP of or and sufficiently large. This is completely result on GP of L comma. What is saying that the fact that you find somebody disconnected is more or less similar to finding them isolated. That's with a small fudge. If n is large enough, you can choose any kappa you like, and that this relationship holds. So this is something I'm not going to prove. If you really want to have the proof, I can refer you to the proof. But at least absorb what is going on. I'm just comparing GP with GP, only two different events. When is GP disconnected over B01 is more or less the same as when there is somebody isolated. This should tell you something interesting. But if I can control the isolation probability, I can control the disconnection probability. That's what is going to happen. Other direction, what did we do? Isolation implied not connectivity. That's how we proceeded in the previous proof. We tried to lower bound the probability of isolation. Here we go in the other direction. So now rest of the effort is to actually upper bound discovery. Then what is the probability of having an isolated node in GP of n comma r? So lemma. This will be if if you've forgotten what lim sub is, don't worry. Think of it. In GP in comma r is less than or equal to where you are then so this is not difficult. Can you indicate the proof? All you have to use is the properties which I listed about. Restriction of GP over B01. So what is the probability that the number of points in GP n comma Rn is equal to K? This is my B01. I'm looking at the PV and KD with density n over these points. So what is the probability that K points lie here? Basic definition of a Poisson point process. What is the probability of finding K points in a region of area A? That was lambda times mu of A e to the power K e to the minus lambda mu divided by K factorial. Area here is 1. So what is the probability of finding K points in this is lambda is n to the power K e to the minus n by K factorial. Now if I condition on having K points here, how are they distributed? Uniform. So is that the same graph as G of K comma Rn? That's the most important fact to notice here. That once I condition, the graph looks like G of K comma R. So condition that K, then we know the K points uniformly randomly. Over P0 is equivalent to thinking of G of K comma Rn. What is G of n comma Rn? N points uniformly distributed with radius. Now I have K points which are also uniformly distributed. So this graph should exactly look like G of K comma Rn. Okay. Now can we use all of that to claim this? So what is probability of isolation in the GP? I've given you all the ingredients. Now you just have to put them together. First condition. What do you get by condition? So P ISO over GP of n comma n is equal to summation K going from 0 to infinity P ISO K comma n to the power K. This is by condition.
What does that probability mean? Probability of isolation.
All I'm doing is I'm just conditioning on the fact that K point multiply with the problem. Now what is this? GP of K comma R condition when the K points is same as G of K comma R. Right? Why am I doing this? Why can't I work directly with P ISO? Why can't I find isolated points in here? If I don't condition, I don't know how they're distributed. So I can't find what is the probability of one point being isolated. See the distinction. Why am I doing all this hard work? If I just look at the Poisson point versus model, and if I don't condition on the number of points, I don't know how they're distributed. So I don't know how to compute the probability that any one node is isolated. Once I condition, there are no the uniformly distributed is same as my graph before, and for which I know what the probability of a particular node being isolated is. So that's why I'm doing this sampling also. Okay, now what should I do? All I need to do is upper bound this. I want to upper bound this one. Give me any upper bound, the simplest upper bound. Sorry, no, that much. I don't have that much.
That will give just one.
Yeah, so that I don't have that much. Sometimes it actually works, but not here. But next best. There's the hint there. Next best to one. How many points there are? K points. Right. So K times what is an upper bound to this? K times the probability that any one of them is isolated. That's clearly a number. And that is how much? K times 1 minus pi r square n to the power K minus 2. Right. So this is less than equal to K equal to K times. Oh, what can you bound this by? Beautiful answer. I'm looking forward to this. This is easy sum. What does it look like?
Same to the analysis.
N times. Yes. That's all. So this is clearly C of n. You plant the value of log n plus Cn by n. That's all. So don't worry about the algebra, worry about what we really did. It's a very clever trick to condition on a number of points falling in the region with the Poisson point process, and that gave a handle on what is the isolation problem. Otherwise, it's difficult to compute the isolation problem, because I don't know how this concept is to. Okay. Now, given that I've done this, what should I do next? Well, what is my goal? My goal is really to compute the isolation probability upper bound. This, I want you to use this somehow. So rest of the idea is as follows. So we have PD of GP that is equal to 1 plus some dropping writing it over and over. So we have isolation of G. That I didn't prove this, but I just stated. Now, what we are going to do is PD of G less than PD of plus some terms which are only depending on n. And this will be the set terms using this. This is what I really want to show. If I can show this, then I can put this together and get what I want. Right. Because in the previous lemma, I have upper bounded this quantity to be e to the minus c bar. Right. When as c bar goes to infinity, that will go to 0. All I need to do is I have this here. I need to do this. Connecting PD of G, PD of G. Plus some terms which are also good. That's the rest of the time. So how do I do this? Any ideas? I want to connect the disconnection probability in G with the disconnection probability in G. So think about a graph G A comma n G K minus 1. What did you say about the PD in this and PD in this? That's really the punchline. Remember, there is no P. So this is just a K uniformly drawn points on disk of radius 1 and K minus 1 uniformly drawn point. I want to think about PD here and PD here. What connection do you think there is? So think about, are they directly related to each other?
We can couple them.
Don't go that far, it's possible. You just intuitively think about, is there any relationship that you can establish? I'm not going to ask you for a proof.
PD in left hand side graph is less than full stone, right?
That's a profound statement. Why is, as I said, I'm not going to ask for the proof, but at least tell me why that is true. There are more points, and Rn is the same, let's suppose.
Yes.
So why do you think that is smaller? So one more point.
Because
But that point also can make it harder to become connected, right? So it's a difficult exercise. On one hand, it's more likely to come and connect two people who are not connected. But at the same time, it could be that the K minus 1 guys are connected This new guy is isolated.
Yes.
So it's a delicate balance between the two. See the problem? That there are key points. So let's say they are all located here. Now new point arrives. It arrives here. It makes it harder for them to be connected because there is one more event which has to be excluded. But at the same time, it could also ease things. So suppose these guys are not connected, and suddenly this point belongs here. So there are one cluster here and another cluster here. And because of the presence of this point, it actually connected. So that's not easy to compare the two. So now think of the next best thing. If one is happening, what does it imply? I've already, the picture is actually telling you. So think of the new guys being isolated. Now can you connect these three things together? So PD on G of K comma R, PD of K minus 1 comma R, and the fact that the kth point is somehow isolated. So you didn't account for, only thing you didn't account for was that the kth point becomes isolated. So account for that. If you had accounted for that, your claim would have been correct. That if it is not isolated, then it only helps. It cannot hurt you. That's all there is to it. Now everything is there. There is PD of K nodes, PD of K minus 1 nodes, and the fact that the kth node is isolated. There are only three probabilities. What's the relationship?
Class.
So PD or G K comma N, yes.
Class A has been.
Let me write this. How much?
100.
That's all. There are many ways to convince yourself that this is right. But what you said was exactly, except for that event you didn't count for, that's precisely didn't count. If it turned out that it was connected, it can only help. That's it. But once you see this, suddenly something should ignite. That I want to go to not K, but to everything. And that everything is G of N comma R. So this is giving you to go from K to K minus 1. I can keep doing this recursively as many times as I like by adding one at a time. So how many such things should I get added? And each of them I know. What are the probabilities that node K is isolated? That I can always compute. So now tell me what control does it give such a relationship? So this is what my final goal is. Yeah, you're saying something?
I still want this thing. I come on to it.
Yeah, so essentially I want to replace K by N.
Yeah.
So in terms of PD of G of n comma Rn, what can you say?
We can use the inequality.
You can keep doing this as many times as you like. How many times you want?
Dimension.
N minus 1 time. Okay. So what will end up getting if you do it n minus 1 times?
If they are lesser equals to BP, we are in zero, so that should be it.
See, you should notice something. I don't want to go all the way to 1. So the same trick as before, like here. I can always condition on k nodes lying in this region and just multiply the probability to it. So I want to go to any particular thing from n to down to k. So I don't necessarily want to go down from n to 1. So k is some number, which is the condition number. So all you really want to do is to go from n comma r to k comma r. So you want to take this k steps. That's essentially what you. What you're saying is not incorrect. It's just that there is only one of such events. I have so many other events to worry about, so I'll write it as a function of k. What will I do? The problem that PD of GP n comma r PD of G times n to the power k. No change. I condition on this to have exactly n point, which is same as g of k comma. And from the previous relationship, what do I get? PD G n comma is equal to n from applying the previous recursion to go from n to k. I'm not going all the way down that one. That's what this relation. K plus 1 to n. The rest of them. So possible. This is fine. This is also fine from the previous recursion. Not clear? Ask me right now. You're almost close to the end of the book. I just took n steps, sorry, how many steps to n minus k steps back from n. How much is this sum? The trivial sum. This is equal to or so that was my dots. Really. Wrote something previously. Here, dot. These are my dots. So what is the final constraint that I have to do? Don't lose track of what you do. It's very easy. There are too many things going on. What have I done here? I've written PD of GP in terms of PD of Gs. And PD of Gs in terms of each other essentially. From an Rn to here. I want to replace it here essentially. Right? That's what I really want. So if I do that, what will I get? I'll get this minus this. Right? Because G of K from Rn is what I want to replace. But this will be exactly n, always n. So the summation will be kind of independent of the index. So that will just simply come out. So planting one get B to be greater than equal to PD of G K comma Rn. And summation, this is probably and the and minus how much? This two. Why this common? Because that is exactly always n. So all of this is nothing but this minus this that comes out common. All you're left with this summation. How much is this? One. The point is, I want to only look at k greater than equal to 0. I don't really want to look at k equal to 0. Because the graph is actually empty.
So you can.
What does k equal to 0 mean here when I'm conditioning on 0 points? This is always 1.
Yeah.
So that's why I should really consider k greater than equal to 1. That's why this is not exactly 1, but greater than equal to 2 minus for large number appropriately. First term essentially contributes half. Because k is greater than equal to. So that takes care of that. How much is this? This you can say something. This is independent of k, so this remains as it is. How much is this? Essentially a to the power k, n to the power k to the minus n divided by k factorial. How much can you say? So this is 1 by pi r squared times simply n. And this is multiplied. Okay, so what have I essentially achieved? I've connected PD of GP with PD of G multiplied by half minus a term which is scaling down as this. So am I done? Remember my strategy. This I know, this I want, so that I can apply this and get back here. So this I have a good grip. I've already shown that this is to be e to the minus c of n. So here, so only thing is these dot dot dots. How much is that dot? This much is the dot. So then r square n is log n by n plus c. What do I get? Is it clear what is going on? If you're missing any piece, let me know, right? That is very important. This I'm assuming to be true. This I have shown right. So from here to here, I can go with plus plus plus. This I have shown to be e to the minus c bar. The c bar is the limit of c. I just have to really worry about how much is this. Then how much is that is here. This bar. So how much is that when r square n is log n by n plus c. That's all you have to do. Can you just tell me order wise what that is?
E to the minus c.
Sorry?
E to the minus c by n.
There's more to it. So this is minus c of n divided by n log n plus c of n. This is what you. Okay, so now where is this going? It's clearly dominating compared to these guys. Limit of Cn is c bar, which is infinity. So this will also be taken. So this dot 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 will also infinity into the minus c bar. In some other scale. And we will go on 0. As long as c bar is there. I don't care how it goes. That's the important point. What we showed in the necessary part was as it necessarily has to go to infinity. If I'm showing however it goes to infinity, I don't care. My probability of disconnection is going to be 0. So the probability of connectivity will be. So the only result I did not prove is this. If you're super interested, it's actually not very difficult. But you can trust it for them. Then the isolation in GP for large enough n is same as disconnection in power. All right, so that's pretty much it for today.